Covers functional dependencies. First, a quick recap of relational design by decomposition. The idea is that the application designer writes mega relations that contain all the information that we want to have and properties of the data that we're storing, and then the system will automatically decompose those based on the properties that are specified. The final set of decomposed relations will satisfy what's called the normal form. And normal forms are good relations in the sense that they have no anomalies and they don't lose information from what was specified in the original mega relations. Now, the properties themselves are defined either as functional dependencies, in which case the system will generate Boyce-Codd normal form relations, or multi-valued dependencies, which we will then yield fourth normal form relations. So this video, as you can tell, is about functional dependencies themselves. And let me say that functional dependencies are actually a generally useful concept in databases, not only for relational design. So for functional dependencies, as we'll see soon, are a generalization of the notion of keys. And they allow the system to, for example, store the data more efficiently when the system knows about functional dependencies. Compression schemes can be used based on functional dependencies for storage. And also functional dependencies, as a generalization of keys, can be used to reason about queries and for query optimization, which, as a reminder, is a very important aspect of database systems, which allows declarative queries to be executed by the system efficiently. By the way, a third use of functional dependencies is for exam questions in database courses, because there's a very nice theory of functional dependencies, as you'll see, and it's quite easy to write questions about them. So the remainder of the video will cover functional dependencies in general, as a general concept, and not specifically to relational design, and then later videos will tie functional dependencies back to design by decomposition. As always, we'll be using as a sample a college application database, and in this case I've expanded the information that we're including quite a bit. We'll be using these same two relations as examples throughout this video and subsequent videos on relational design. In this case, we're going to look at two relations, one with information about students and then a separate one with information about where they're applying. The student information will have social security number, the student's name, their address, and then three attributes about their high school. We'll assume there's unique codes for high schools, but then they also have a name and are in a city. Finally, the student's GPA and a priority field for admissions that we'll see in a moment. For applications, we'll have the student's social security number, the college name they're applying to, the state of the college, the date of application, and the major. Not all of these attributes will even be used in this video, but like I said, this will permeate several videos as our running example. To motivate functional dependencies, let's focus on the student relation and specifically on the GPA and priority attributes. Let's suppose that a student's priority is determined by their GPA. For example, we might have a rule that says if GPA is 3.8, greater than 3.8, then priority is 1. If the GPA is, say, in between, let's say, 3.3 and 3.8, then we'll set priority to be equal 2. And let's say if the GPA then is less than 3.3, then the priority value is 3. So if this relationship is guaranteed in our data, then what we can say is that any two tuples that have the same priority are guaranteed to have the same GPA. And let's formalize that concept. So I'm going to write a little logical statement here to formalize the concept. I'm going to use the for all symbol from predicate logic, and I'm going to say if we have any pair of tuples, so for all t or u, those are tuples, in the student relation, then if the t and u have the same priority, so I'll say, let me fix that, they have the same GPA. So if t.gpa equals u.gpa, then, and this is the logical implication symbol, then t.priority will equal u.priority. So this logical statement is, in fact, the definition of a functional dependency, and we would write that functional dependency as GPA arrow priority. So that says the GPA determines the priority, or any two tuples with the same GPA must have the same priority. So that was a specific example. Now let's generalize our definition. So let me replace GPA and priority here with just two attributes, A and B, of, say, a relation R. And then we'll also need to modify our definition. So you can see I've erased the specific attributes and relation, and I'll just say for every T and U in our relation R, if T.A equals U.A, then T.B equals U.B, and that's the definition of the functional dependency A determines B for a relation R. Actually, I'm going to generalize this definition even further because functional dependencies don't always have to have one attribute on each side. They can actually have a set of attributes. So now I write A1, A2, AN on the left-hand side. These will all be attributes of relation R. And on the right-hand side, B1, B2, BM, again, attributes of R. Modifying the formal definition in red, now I can't use the dot notation anymore, so I'll use a square bracket, and I'll write A1 through AN equals U square bracket A1 through AN. Whoops. So what I'm saying here in this case is that the two tuples T and U have the same values for all of the attributes A1 through AN, and if they do, then they will also have the same values for B1 through BM. We'll be getting to some concrete examples soon. Just one last bit of notation before we move on. For simplicity, I'm going to often in the video abbreviate a list of attributes or set of attributes by using a bar. So I'll write A bar to indicate a set of attributes A and B bar to indicate a set of attributes B. And again, this is just for convenience. So we've seen the motivation for a functional dependency in a relation. A functional dependency for a relation is based on knowledge of the real-world data that's being captured. And when we specify one, just like specifying keys, all instances of the relation must adhere to the functional dependency. So just to summarize functional dependencies, we say that a set of attributes A functionally determines a set of attributes B if, again, anytime tuples agree in their A values, they also agree in their B values. And let's say that our relation here R has the tuples in A, the tuples in B, and also a few more attributes. We'll call those C. So let me draw a picture of a relation now here that has those attributes in it. So we'll have here, let's just 3 columns, but again, these are multiple attributes, and these are the attributes A, these are the attributes B, and these are the attributes C. And if we put in a couple of tuples, then what we'll say is if we have 2 tuples here that have, and I'm going to use a bar even for these values in the tuples, if we have 2 tuples whose A values are the same, then their B values must also be the same. And we're going to be using this type of template for some reasoning later on. But we're not saying their C values have to be the same, so we could have C1 and then different C values here as well. But again, if we specify this functional dependency, we are saying that every instance of our relation must satisfy the condition that if the A values are the same, then the B values are also the same. Finally, let's come back to our example. And I think when we start writing functional dependencies for our actual relations, it'll give you a good idea of what they're really capturing. So let's write a few functional dependencies for our student relation based on what we expect to be true in the real world, in the data that we're capturing in the relation. So here's a first example. Social security number functionally determines S name, so the student's name. So what we say, if we have multiple tuples about a particular student, they have the same social security number, say at 2 tuples about student 1, 2, 3, we're expecting them to have the same name. In fact, we're requiring them to have the same name. And presumably, because 1, 2, 3 is sort of identifying the student, that would be a natural functional dependency that would hold in this case. And similarly, we would expect social security number to determine address, although we're already making an assumption about the real world here. If we have this particular functional dependency, then we're saying a student doesn't move. They don't have multiple addresses. Every tuple that describes that student by their social security number will have the same address. Let's go to the high school and see what might be going on there. So I mentioned that the high school code, what I'm trying to capture there is a unique code for each high school that might be filled in college applications. Then we would expect the high school code to determine the high school name. Every time we have the particular high school code, maybe for different students, it would have the same name, and also it would have the same city. So that's an example of a functional dependency with 2 attributes on the right-hand side. Now, let's look at one that's a little more complicated, which is one that has 2 attributes on the left-hand side instead. That actually turns out to be a more interesting case. In fact, in this particular case, we can probably reverse the arrow and have a functional dependency in the other direction. If we have a combination of high school name and high school city, I'm going to assume that's unique, that there's never 2 high schools with the same name in the same city. And if that's the case, if that's unique, then we would expect a functional dependency to the high school code. Anytime we have the same name and city, we're talking about the same high school, so we should have the same code. What other examples do we have? If we assume that there's 1 GPA for each student, then we'd have the social security number determines the GPA. And we already talked about GPA determines priority. And another example, actually, if we put these two together, we should see, well, if we have the same social security number twice, then we should have the same priority. And you might be thinking, well, that's kind of a transitive rule that takes these two and produces that one. And indeed it is. And we'll talk about rules for functional dependencies later. And there may be more in this case. Now let's take a look at functional dependencies for our apply relation. Actually, this one is a little trickier. It's even possible there are no functional dependencies at all. It really depends on the real-world data, the real-world constraints. One possibility, for example, is that every college has a particular single date on which it receives its application. So if that were the case, then we'd have the college name determines the date. In other words, every application for a particular college must have the same date. Another constraint might be that students are only allowed to apply to a single major at each college they apply to. So if that were the case, this is another one with two attributes on the left-hand side, we'd say that the social security number together with the college implies the major. In other words, we cannot have a student and college combination with two different majors, and that captures that constraint. Maybe we have a constraint that students are only allowed to apply to colleges in one state. That seems rather unlikely, but I was struggling to find functional dependencies for this case. In that case, we'd have this functional dependency, again saying a student could only apply to colleges in a single state. For the apply relation specifically, again, it's really the real-world constraints that drive which functional dependencies hold for the relation. But it's important to understand those constraints so they can be translated to functional dependencies, which then can drive good relational design. So I've alluded a few times to the fact that functional dependencies generalize the notion of keys, and let's make that connection explicit now. Let's suppose we have a relation R, and R has no duplicate tuples. R has some attributes A, and it has some other attributes, let's call those B. And let's suppose that we have a functional dependency that A determines all of the attributes in the relation. Now let me draw a picture of that. So here's our relation R with attributes A and attributes B. And now let's suppose that we have two tuples with the same values for A. So we'll just write those as little a bar. And now let's see what happens with the B values. We'll make them B1 bar and B2 bar. Because we have the functional dependency, the equal values here for A say that B1 and B2 have to be equal. So B1 equals B2. Let's just erase the little 1 and 2. But now we've generated duplicate tuples. So what the functional dependency tells us in that case is that these two tuples are actually the same, or rather we cannot have two separate tuples with the same A values. So we cannot have two separate tuples with the same A values is exactly what it means for A to be a key. Now again, this is only the case when we have no duplicates in R. But if we have no duplicates, if a set of attributes determines all the other attributes, then those attributes are a key. So here are a few other definitions related to functional dependencies. We have a notion of a trivial functional dependency. A functional dependency is trivial, A to B, if B is a subset of A. And let's just draw a little picture of what that means. So here we have our attributes A, and then we're saying, and that's all of the attributes here, and what we're saying is that B is a subset of A. So in other words, some portion of these attributes here, we'll just mark that in purple here, are attributes B. Well, it's pretty obvious that if two tuples have the same values across their entire expanse here for A's, then obviously they're also going to have the same values for just this portion here, the B portion. So that's why it's called the trivial functional dependency. So a non-trivial functional dependency is a functional dependency that's not a trivial one. By the way, FD is a common abbreviation for functional dependency. So if we have A determined